So last time we left off talking about the gas turbines for aircraft propulsion, did we not? And I even talked about this setup where we had a diffuser, compressor with some isotropic efficiency, combustor, turbine with some isotropic efficiency, and a nozzle. And a typical assumption is that the diffuser is isentropic, no efficiency needed. Same for the nozzle. So let's spend a little time talking about the diffuser. I'd introduce a control volume for the diffuser, and then I apply a balance equation, first law, second law analysis. When you do the first law analysis, you'll find out that the inlet enthalpy plus the inlet kinetic energy, don't forget the inlet kinetic energy, that's the purpose of the diffuser, to slow it down so it has a high speed coming in, high kinetic energy. Isn't the kinetic energy coming in 1/2 velocity of the inlet squared? I'm staying with the textbook. This textbook uses subscript A for state coming into the diffuser. Okay. And then that's converted to the exit enthalpy. So you're going to have a higher H on the exit of the diffuser. And then you want to think about, also that's the first law. The second law is very trivial. You'll get SA is equal to S1. What does that mean? It's isentropic. There's no irreversibilities, steady flow through, no heat transfer. It's isentropic. And then you try to analyze it and you say, well, I know that the temperature is going to change. The temperature one, that must be greater than the temperature inlet. And I know the pressure is going to change. That must be greater than the pressure inlet. But what is the equation to calculate the T1 and P1? You have two approaches to the problem. You can go with constant specific heat, or you can go with specific heats are a function of temperature. We talk about that as being variable specific heats. All right. So if it's constant specific heat, can I rewrite this energy equation such that it's the H1 minus HA is equal to the kinetic energy at A? Depending on how fast it comes in, well, there's going to be an increase in the enthalpy. I'm going to convert all that kinetic energy into increasing the enthalpy. So this is C sub P, T1 minus TA equal to KEA. Hey, that's my equation, how to get the temperature, not at A. Temperature at 1, it's the incoming temperature plus the boost due to converting that kinetic energy at A into an energy balance back into enthalpy. So there you go. The one thing you have to remember is the unit conversion when you're doing that. Right here is 1,000 meters squared per second squared is 1 kilojoule per kilogram. You basically need that right in here where you're using the speed and then you're using the kinetic energy. All right. How about the pressure? Well, we assumed that it was isentropic, did we not? So there's many relationships for an ideal gas, constant specific heat undergoing isentropic process. One of them is that we have that the exit temperature divided by the inlet temperature is equal to the exit pressure divided by the inlet pressure raised to the power K minus 1 over K. You say, I'd like to use that equation. Yeah, you can. But what we do is you get P1 is equal to PA times T1 divided by TA to the power K over K minus 1. You just use that equation, but this time you're solving for P1. How about now variable specific heat? Maybe I'll leave a little more room over here. Variable specific heat. Well, you're thinking when you use variable specific heat in your mind for this textbook, there's a table. The table is A20, 2? And in that table, you have a column for temperature, bunch of temperature values, a column for enthalpy, a bunch of enthalpy values for air, and then you have internal energy U, but let's leave that off. And then we have this V sub R and P sub R column, and those two columns are only if it's an isentropic process. That's the only time we use the V sub R and P sub R column, true? All right. Well, you're going to get good at using these three columns, the T, the H, and the PR. Okay? So what you do, for variable specific heat, you're saying, okay, I know the inlet temperature, T1. That's true. So I can look up, I'm going to write it like this. I'm going to look up PR at A is equal to PR as a function of TA. Get H at A is equal to H as a function of TA. Same thing. I'm coming down at this temperature. I'm reading off an enthalpy and I'm reading off a PR. That's for A. Okay, then we can use this energy balance that H1 is equal to HA plus that kinetic energy at A. So now I know the enthalpy at the outgoing at state 1. This is tricky, but hey, sometimes variable specific heat is a little tricky. Go into table A22, search for the enthalpy, okay? Maybe that enthalpy will be right here, because isn't it greater than H, if visually I'm trying to draw this one as H at A, and then this H1 will be greater than that one. It'll be further down the table. And then what you do is interpolate. What do you mean interpolate? Go ahead and say, give me the temperature at 1 as a function of enthalpy at 1 out of that table. And also get me PR1 as a function of H1 in the table. Once you've done that, you've gotten now the temperature. That's a good one. Bingo. There you go, the temperature for constant specific heat. That's how we get the temperature for variable specific heat. But we need to get the pressure, but it's right in front of us. So the pressure at 1 is equal to the pressure of the incoming A times PR1 divided by PRA. And there you go. That's how we get the pressure at the exit of the diffuser. And here it was assuming constant specific heat. Will they give you the same answer? Pretty close, but they won't be exactly the same or different approaches. One accounts for temperature-dependent specific heats, one doesn't. Makes sense? So I tried to summarize this right here. So I leave it up for a second or two. Second law, first law. If you go constant specific heat, it's kind of going this way. It sure does feel a whole lot different when you use variable specific heats, doesn't it? It sure does feel a lot different. And you can get that pressure on the exit using the relationship that the ratio of physical pressures for an isentropic flow in air is equal to the ratio of the PRs in that table. And then if you needed, you can just look up the exit temperature T1. But really the key property is going to be that H1. Maybe I should have emphasized that. You're going to look up, well, you calculate H1 right here is equal to H of A plus the kinetic energy at A. That's H1. All right. Yeah, you see I've written it right there. Okay. Let's press forward. You need to be able to analyze each of those components. The next component is the compressor. Because we've analyzed the compressor so much, I thought I, in the interest of time, would say, you know how to do that. Both for constant as well as specific, variable specific heats. Same thing for the combustor. These two components are so similar. But what I want to do is spend a little time about the turbine, because this turbine's a little different than the analysis that you've done already. So coming from the compressor, we know that the work needed to run the compressor, and I'm going to leave that as a positive entity of the work needed to run the compressor, is going to be the difference in the enthalpy at the exit of the compressor minus the enthalpy at the inlet to the compressor. That's true. We do a control volume analysis around this turbine. You don't even have to worry about that isentropic efficiency right now. It's just the same thing. You'll find that the work positive out of that turbine is an enthalpy difference. It's H at 3 minus H at 4. The criteria now for the jet engine is that what comes we only get enough out of the turbine to drive the compressor. So they have to match. In the traditional power Brayton cycle, W turb out of the turbine is a lot larger, so it can drive a shaft. All right. Same thing with the second law. The second law is it's isentropic. S3 is equal to S4. Okay, let's do this. How do I solve for, let's say, the temperature at 4 and the pressure at 4 if I assume constant specific heats? C sub P is equal to a constant. And then likewise, how about C sub P is equal to a variable? It's variable specific heats. Let's do it both ways. Let's focus on one first. Well, I would come over here and I'd say, well, that work in the compressor was really C sub P times T2 minus T1. The focus shifts away from the enthalpies onto the temperatures. And likewise, W in the turbine is C sub P T3 minus T4. So when I put them together in this equation, I get that C sub P T2 minus T1 is equal to C sub P T3 minus T4. I can cancel the C sub P's. And that you find that the exit temperature T4 is equal to the inlet temperature. Let me do this. Minus T2 minus T1, that temperature difference across the compressor. All right. Now, what happens if they gave me an isentropic efficiency of this turbine? Well, this is a little trickier, isn't it? Because what's our equation? The isentropic efficiency of the turbine is a ratio of the work that the compressor would have produced if it had been isentropic flow through the compressor or the turbine. Why did I put a C there? It's a T, turbine. Divided by the work, the turbine actual. True? So you can say that the work that the turbine would have done isentropically is the isentropic efficiency times the work the turbine did actually. The assumption is that you're going to have the same pressure drop across the turbine. The actual pressure drop matches the quote-unquote isentropic flow pressure drop. You're not changing them just because you have an isentropic efficiency. You just only have one pressure drop to consider. Okay, so what happens here is this is the 3 minus T4S equal to the isentropic efficiency of the turbine times T 3 minus T4 actual. Well, here's the T3 minus T4 actual is T2 minus T1. So maybe, it depends on how many substitutions you want. You can put that efficiency like that, and that's T2 minus T1, fine. And then you can bring this minus, and then this is T3 equal to T4S. You can solve for T4S. You have a question?
For the efficiency, isn't it the other way around?
Oh, yeah. I'm sorry. It's absolutely. Thank you very much. A over T, right? A over S. A over S. All right, so that then switches all these to divide by eta of the turbine, eta of the turbine, eta of the turbine. There you go. Now it's better. Thank you. You probably had your hand up. It was starting to grow weary, huh? How many other people were trying to get my attention? Sorry. Yeah. All right, so we were able to get T4S. Once you get T4S, now you can say, I know what the P4 has to be. P4 is equal to P3 times T4S divided by T3 to the K over 1 minus K minus 1. Using our familiar equation, but we invert it a little bit, right? What's our familiar equation? It's like T2 over T1 is equal to P2 over P1 to the K minus 1 over K. That's generically how it's written in our equation sheet. Okay. So, and then this is really like a P4S, which is the same as P4 actual. I know it's sometimes better to think of, the assumption is that if it would have been isentropic flow through that turbine, it would land at the same pressure as if it's the actual flow. And this is our equation for T4S, and this is our equation for T4 actual. All right, well, do you really want to take and twist your head around a little bit? If you do it with the table, A20, what is it, 23, for variable specific heats, you get master at figuring out, okay, now I'm coming in with enthalpy. No, now I'm coming in with temperature. Okay. The actual enthalpy at 4 is equal to the enthalpy at 3 minus the enthalpy at 2 minus enthalpy at 1. I think that's maybe pretty trivial there. So we get our enthalpy at 4, what it needs to be. Okay. It's like also we were able to calculate what the turbine work actually needed to be. That's the H3 minus H4. Okay. So then what is the turbine work if it would have been isentropic flow? It would have been that turbine work actual divided by the isentropic efficiency of the turbine. This gives you equation for H4S is equal to H3 minus, if you want to write it like this, H2 minus H1 over the efficiency of the turbine. But you get an H4S as well as an H4 actual. The H4S is going to be less, lower. I mean, it never really does expand isentropically. We're just backing out what it could have been. All right. Then you have this H4S. So think about the table A22 or 23. What is it? I lost my number. A23. And you have the temperature, the enthalpy, the piece of R. Here, you're coming in with an isentropic. You read across for temperature and piece of R. So you can get that the piece of R at 4 is equal to, and that's 4S really, but gets redundant. It's equal to piece of R at H4S. All right. You already got the piece of R at 3 because you know the temperature and enthalpy at 3. All right. And so now we get finally the pressure at 4 at the exit is equal to the pressure incoming times the ratio of PR4 divided by PR3 using that pressure ratios. If you wanted to, you don't really need the temperature, but if you wanted to calculate the temperature, you could. You just basically are going to be getting T4 is equal to the temperature evaluated H4S. It's like we come in with the enthalpy, we get the piece of R, we need that, but you could also get the temperature. Does that make sense? That was probably the hardest part of it. Because that pressure, people struggle with. How do I get that pressure at the exit? Here's a summary of it. I think it's pretty correct. I mean, I just actually, after the 8:30 class, I thought I could improve a little bit the presentation. And the nozzle. The same thing. You want to do a first law, second law for the control volume around the nozzle. And what we find is that S4 is equal to SB, using the subscript B for the exit state. And then the enthalpy at 4 is equal to the enthalpy at B plus the kinetic energy at B. We're really interested in how high that kinetic energy at B can be because it gives us more thrust. Okay, so if you have constant specific heat, how do we analyze this problem? Well, first of all, this pressure at B is known. It's back to the pressure at A. And we did a lot of work analyzing the turbine to get the pressure at 4. Yeah. And so once you realize that, you did a lot of work with the turbine to get the pressure at 4, You know it's greater than the pressure at B, and the pressure at B is known as well. That's equal to that. What you can do is you can say, well, I can get the temperature at B. That's equal to the temperature at 4 times the pressure at B divided by the pressure at 4 to the K minus 1 over K. Isentropic flow, ideal gas, constant specific heats. Then we use our energy equation. Maybe I rewrite that like this, and I say the C sub P times the temperature at 4 minus the temperature at B is equal to the kinetic energy at B. Hence, the kinetic energy at B, it's almost too trivial, isn't it? Well, there it is. I mean, there's the kinetic energy at B. I just calculated the temperature at B, and the temperature at 4 was a result from the analysis of the turbine. Okay. So I have both the pressure at B, the temperature at B. If I wanted the speed at B, you take 1/2 VB squared is the kinetic energy at B. So when I want to get it back, I just multiply by 2 and take the square root. And don't forget your unit conversion. 1,000 meters squared per second squared is a kilojoule per kilogram. Okay. And I don't know much more to say on that one, is it? It's pretty straightforward. How about variable specific heats? Well, okay. What we're going to do is we're going to have state 4 pretty well known. We know that the piece of R at 4, that's piece of R at the state 4, which really we knew by the enthalpy at 4, didn't we? Okay. And we know that the pressure at the exit B, and so what is the piece of R at B is equal to piece of R at 4 times PB divided by P4. So I'm able to get the PR at state B. I think about going into the table. Maybe I put it over here. Table A23. I keep remembering. Is it 23? Yeah, I think so. I don't know why. Sometimes my brain stops working on certain things. All right. So now we're thinking, oh, this time we're going to come in at this piece of R, interpolate across to get the H, and if you wanted to, get the temperature. Okay. So you come across and you can get H at B is equal to H as a function of PRB. And if needed, the temperature at B, that's temperature PRB. All right. Once I have the H at B, then the kinetic energy at B is equal to the H4 minus the HB. And then V sub B is equal to 2 times that kinetic energy at B square rooted. You ready to do it in Excel? I wanted to jump into Excel, but I wanted to make sure you know the equations that we're implementing in Excel. Right? So I think that's what we have here. The same equations that I just described. Okay. So this is the problem that we had last time. So we have a jet engine, low pressure, low temperature. It's flying at high altitude at a pretty good speed. It has a good mass airflow rate coming into the jet engine. It has a diffuser. Then the compressor with a pressure ratio of 11. As a negligible pressure drop through the combustor, standard assumption. At the turbine inlet, that means it's been heated to 650 K in the combustor. The isentropic efficiency is 85% for the compressor, 90% for the turbine. So they're different values. We're going to deal with it. And the work developed by the turbine equals the compressor work input. The diffuser and the nozzle are isentropic. The operation steady state kinetic energy is negligible except for at the inlet and exit. And do an air standard analysis with a certain value of K and a certain value of C sub P. And the velocity, calculate the velocity at the nozzle exit and the thrust. So at this point, I'm going to go to Excel. All right. Yeah, okay. So I always start with a comment like a turbojet, and it's a constant specific heat. And then because it's a comment and I want it to be really stand out, I may bold it, increase the font size a little bit, play with it a little bit, make it big and bold. All right. And then I have a lot of information that's given to me in the problem statement. What's that pressure ratio? Isn't it 11? Yeah. And then we're going to work with K and C sub P. Let's put C sub P there, kilojoules per kilogram Kelvin. C sub P, what, 1.10? Okay. Let's put K over here. K is equal to, value for K, 1.35. Let's put efficiency of the compressor is 85%, and the efficiency of the turbine is 90%. Yeah. And then both of these we'll put percent. Make it look good. All right. And we have the mass airflow rate, m dot, kilogram per second, and I think that was 25. And let's jump into it. I like to make a table of states. And since I've scoped out the problem, we know that we're coming in with state A, and then we go to state 1 after the diffuser. Then through the compressor, I need to do it isentropically as well as the actual exit at the end. That's my notation. Then at the exit of the combustor, then isentropic expansion to state 4S through the turbine, then 4 actual, and then B is the exit. Now, I have to always play around with this, so make it look a little better, right? And then I'm going to put my pressure in kilopascal. You could put it in bar if you like. Temperature in Kelvin, that's often the best. And we really don't need for anything else for constant specific heat. We really don't need another common couple. But we'll put the kinetic energy in kilojoules per kilogram, and we'll put in the velocity in meters per second. All right. So our input value is 26 kilopascal, 230, and 180. And then after the combustor, the temperature was 650. True? All right. All right. So the first things first, let's convert that speed to kinetic energy. So that's going to be equal to 1/2 v squared. So it's equal to the velocity squared, and then divide by 2. Common error, student would leave it like that, but we're not the common student, are we? Because that unit's meters squared per second squared. So we'll divide by another 1,000, or a lot of times I just divide by 2,000. So it's 16.2 kilojoules per kilogram. That's the kinetic energy. Okay. From our energy balance, we know that the temperature at 1 goes up, doesn't it? And it goes up, it increases from 230, I'm implementing my equation, by that kinetic energy divided by the specific heat constant pressure. So it goes up. I'm going to clean up the digits here so it looks a little better. Doesn't it go up to like 244.7? You just took all that kinetic energy, converted it into enthalpy conservation of energy. It's isentropic, so we can get that the pressure increases, the inlet pressure, times the ratio of temperatures, T divided by T, to a power. And at this point, I remember what I wanted to do. I wanted to put something over here in a cell that was K minus 1 over K. So I'm just going to temporarily grab that cell, which is nothing. I'm going to come over here and I'm going to say this is K minus 1 divided by K and I'm going to compute it. I'm going to fix it. I know I have an error still. So K minus 1 divided by K, K in return. And then actually right now I don't need that one. I need the reciprocal of that, don't I? K divided by K minus 1. So that's equal to 1 over this value. I'll just put those there so I can do it. So when I come over here to this exponent, I'm putting it on the ratio of temperatures, and it's not the first but the second one, isn't it? So there's my pressure. My pressure is 33 kilopascals at the end of the diffuser. I look at it, looks reasonable, temperature is up, and the pressure is up. Okay. We're not going to do the kinetic energy and the velocity until we get all the way down to B again. So the rest of these are going to be 0 blanks in there. All right. Now, we think about our pressure ratio that's specified in our compressor. So our outlet pressure will be 33 times that pressure ratio. Well, that's going to be the same pressure, and that'll be the same pressure through the combustor. So I just fill in all those pressures. Okay. If it was isentropic expansion, what is my temperature after, not expansion, compression, after the compressor? Wouldn't it be the inlet times the pressure ratio raised to the K minus 1 over K? Yep. So there it is. That's our temperature if it would have been isentropic. But unfortunately, we have this isentropic efficiency. So it's going to be the inlet temperature plus the isentropic temperature increase divided by the isentropic compressor efficiency. It's going to be hotter coming out. There it is. Okay. Is that a little easier to see? I zoomed it up a little bit. A little easier? Or keep going, Professor. No, can't do that. That's about the maximum we can go. All right. All right, now we're going to come down here, and we have to focus on the temperature that actually comes out of the turbine. And that temperature that actually comes out of the turbine will be lower than the inlet temperature by how much? Because it's constant specific heats, it's the same temperature change as what the compressor went up, which is, it went from, it went here minus that. Okay, so then our isentropic temperature would be the inlet temperature minus the same delta T that I just had, which was, I can draw it like this temperature minus that temperature. And then we have divided by the isentropic efficiency of the turbine. We just implemented the equations we derived, and they're a little conceptually challenging. All right, but I think you see the pattern. It's like get the temperature at 4A, then the temperature at 4S. Now walk over here and get finally the pressure, because this pressure is going to be the inlet pressure times the ratio of the temperatures, the T divided by this T, all to the power not K minus 1 over K, but K divided by K minus 1. And that'll get all the way down to 43.2 kilopascal. And the assumption is these two pressures are the same. That's probably conceptually where a lot of students, if they think too hard about it, they're like, why are those two pressures the same? But that's the way the analysis is done. I just encourage you, if you're baffled by it, think about it more. Okay, all right. But this is what drives the flow through the nozzle. So we can go from 43.2 to 26 to try and get it to have a high exit speed. All right, Well, if that's our pressure ratio, then our exiting temperature, isentropic flow, will be that temperature times the ratio of pressure that we can actually go through. Whoops, it's going to be 26 divided by 43.2, all raised to the power K minus 1 over K. So this is our exit temperature. It's coming out cold, but it's coming out fast. All right, so we can finally get our kinetic energy difference. That kinetic energy is the inlet kinetic energy at 4A into the nozzle minus the exit temperature. And I need to use the specific heat, don't I? So let's put our C sub P times that temperature difference. And then that gives us our kinetic energy. Let's clean up digits a little bit. All right. And now we can finally get our exit speed. Our exit speed is the square root of the kinetic energy times 2,000. Oh, too many equal signs. So it comes out 330.9. So maybe we put our answers over here. We're interested in V exit in meters per second, and the answer is 330.9, and that was our answer to part A. And our force, our thrust in newtons, what is that going to be? Well, that's going to be the difference. It'll be the mass flow rate. Where did I put mass flow rate? Right here. Times the difference in the speed, exit minus the inlet, and that will have units of Newton, won't it? So there you go, and that's the answer to part B. And so maybe I just box it. Hey, look at that, even boxes it in Excel, and even color code it if you like, maybe a light color. There you go. So that's how we solve the problem. Somebody says, I don't think that's, what you could do is you could do this. You could get an average temperature for all these temperatures right there. About 400 Kelvin, right? Probably I can get a C sub P at a function of temperature. So what I'm going to do is I'm going to get C sub P for air. C sub P, what did I just do? When I want to get a function, C sub P underscore T for air, guess what? I can. I'm going to evaluate that at 400. And it comes in at 1.015. See that? Likewise, K. I'm going to get K as a function of temperature. And I'm going to say K for temperature, air, blah, blah, blah. It anticipated me. 400. And it looks like this. So what I'm going to do is I'm going to go plink, plink, plink. And I'm going to say I'm going to change these values. Instead of using 1.100, I'm going to use an average for all those temperatures of 1.015. So look at the numbers, memorize them. Now they changed. As well as the K, 1.395 or 4. Okay. So you can actually make this constant specific heat a little closer. They didn't change much, did they? Didn't change much, but it changed a little bit. Okay, so we'll rename this sheet to the constant. And are you interested in more pain? Always. Hey, you're in mechanical engineering major. Turbo, guess what? Variable specific heats, right? So I'm going to reuse a lot of this. So what we can do is say, you know what? I'm going to delete that. I know it messed up my sheet, but it's like, don't be tempted to ever use K or C sub P in the variable specific. Just delete all this stuff, right? It's like burning the ships. You're not returning. You're into this. All right, so this pressure, temperature, and the speed, and that hasn't all changed. But now, how did we solve this problem again? Right? So what we probably want to do is we probably want to go ahead and add a column and add another column. There are going to be two new columns. One is going to be the H column in kilojoules per kilogram, and one is going to be our PR column, which is dimensionless, but for isentropic flow. And so we can do this. H as a function of temperature for air, and there's our temperature, so might as well start populating it. And then our PR is a function of temperature for air, and right there. And that's not enough digits. I'll have to scoot over to see. Anyway. Okay. So what do? How did we solve this problem? Well, it was from an energy balance, and we said that that enthalpy at state 1 was the combination of the enthalpy coming in plus that kinetic energy's contribution. So there you go. So it's like this is the key to state 1. So now if I wanted to, I could look up the temperature as a function of enthalpy for air. And like that. And then I could get P sub R as a function of enthalpy for air. Right? And this pressure, now I can actually get, knowing my inlet pressure times the ratio of PRs, this PR divided by that PR closed parent. I probably want to put another couple digits on this there. So we're at 33 kilopascal after the diffuser. Okay. Then we go to isentropic flow through our compressor. Well, it's a different equation, isn't it? So what it is this PR is the pressure ratio times the pressure rate at the inlet. And now the key is I look up, if I wanted to, the temperature is a function of P sub R of air. That's information, but really the key is the enthalpy. Enthalpy is a function of P sub R for air. All right. Now, that's the actual change of the enthalpy if it would have been isentropically 100%, compression, but it's not. So the actual is going to be this plus the isentropic work divided by the isentropic efficiency. So the enthalpy is higher at 2 actual. Now I can get the temperature if wanted to as a function. Temperature is a function of enthalpy. I don't know why. That always bothers me. Some student tried to help me this morning and figure that out, but it won't work on my computer. And then this is PR as a function of, actually we don't even need that PR at this point. There's it is. You didn't even need that temperature, but we have it. Okay, then it's heated up to 650. We're going to need that PR. PR is a function of temperature. All right. And the same thing. We have to get the, I need to get the enthalpy here. Enthalpy is a function of temperature for air. All right. I need to calculate the exit enthalpy. That exit enthalpy is starting here, and you take off what the compressor needed. There. Okay. At that point, I could look up the temperature. I don't really need it, so I'm going to leave that off. Okay, don't need that. Okay. What I do need is P sub R as a function of enthalpy. Right. Oh, that's not right. What I need to do is I need to get the isentropic enthalpy, which would be this enthalpy minus the same amount that I had before, this one minus that one, but I divide by the turbine isentropic efficiency. Now I can get the piece of R as a function of enthalpy for the air. Knowing these two pressures, I can finally get the pressure at the exit. It's equal to this pressure times the lower PR divided by the upper PR. And it's very similar to our other values. And so we have about, what is that, 10.2 kilopascal to drive it through the nozzle. Okay. So this is our enthalpy coming in, and this is our actual pressure change. I do need that pressure ratio, don't I? I do need it. Okay. All right. So if we're going to have that actual pressure drop, then we can calculate the PR at the exit. That's equal to PR at the inlet times the lower pressure at the exit divided by the upper pressure. So there's your PR. You can finally get the enthalpy. Enthalpy is a function of PR for air. Aren't you glad you asked for this? Maybe we should have said, hey, who wants to see all this? And have them sit in the front row. So there it is. If you want, you can get the temperatures. Should I get the temperatures? Fine. The temperature is a function of enthalpies for the air. A tab. And then put it there and then just scoot it in. Dummy. Fine. And once I have that formula, I can percolate it up just like that. Boom. There's your temperatures, but we really don't need them. Actually, isn't it interesting? The average temperature of the cycle is about the same as what we had with constant specific heats. All right, so we have that, but we need to get our kinetic energy. Our kinetic energy is the difference between this one minus that one. And then our exit speed is 260 meters per second, and that's our thrust. This was not needed. We don't need that. That was copied over. So this is using variable specific heat. If I come back here and I just grab snipping tool so I can compare, I'm just going to grab those. Come over to the other sheet and paste it somewhere and take a comparison. If you use constant specific heats with reasonable values, it's pretty accurate. All right. So how many people are following along on their laptops? Okay, with that, I think we're done for today. I'm going to save this. Thank you for your attention.